Suppose we are in a world of vacuum where gravity does not exist. There is nothing in it, but only we as the observer and two neutral, perfectly conducting metal plates. The plates have a side length of 1 centimeter and are placed parallel to each other with a distance of 1 micron. What will happen? You may think, if there is no gravitational effect according to Newton's first law, nothing is really going on, right? Well, it turns out that things are not that simple. In 1948, a Dutch physicist Hendrik Casimir discovered that for such a pair of hypothetical metal plates, there would be a mysterious attraction force acting on the plates, pushing them together. This attraction phenomenon is called the Casimir effect. According to his calculation, the attraction force between our plates would be approximately 1.3 times 10 to the negative 7 newtons. So where does this force come from exactly? Well, it actually arises from extremely complicated quantum electrodynamics interactions in a vacuum. In the rest of the video, I will try to explain the mystery of the Casimir effect to you in an easier manner. In the view of modern physicists, a vacuum is not really that empty as we usually imagine. It can be perceived as a sea of electromagnetic waves and quantum physical interactions. A straightforward model to visualize such a vacuum would be a space full of vibrating strings representing the electromagnetic waves, oscillating freely with all different wavelengths and transmitting energy in space. And for the metal plates, as perfect conductors, since when there's an external electric field in the environment, the free electrons in the plate will behave to completely counteract the external electric field. The metal plates can be seen as so-called boundary conditions, or walls that those analytical vibrating strings tie to, rendering the magnitude of the electromagnetic field to be zero locally. Suppose we use such a metaphoric model to our question. In that case, we can realize that in the region between the metal plates, due to the presence of boundary conditions, the strength of electromagnetic waves have to be zero on the inner surface of the plates. Thus, the propagation of the electromagnetic wave is, in physicists' language, quantized between the plates, meaning only a series of waves with discrete wavelengths can exist. Meanwhile, outside the plate pair, all electromagnetic waves with continuous wavelengths can propagate freely with no restraint. As a result, according to special relativity, because electromagnetic waves can carry momentum and radiation pressure, we can say loosely that the two metal plates in the problem will experience unbalanced bombardment from an infinite number of photons from both sides, resulting in attracting forces acting on them. And the resultant net force to the plate is what we call as the result of the Casimir effect. Though the Casimir effect seems trivial to our real life, it actually has a lot of potential applications in many fields. In academia, it is a crucial theory to help us understand the answers to some of the ultimate questions like what dark energy and dark matter actually are, or what kind of geometric structure of our spacetime really is. In industry, especially in nanotechnology, engineers have to consider how to prevent the effect of Casimir force between movable metal parts from sticking themselves together, and also how to use the Casimir effect as an energy source to drive microelectronics machine. So that's all about the Casimir effect in today's video. Thank you for watching.